Hello, everyone, and welcome to the California Fire Science Seminar Series. I'm Michael Gollner from UC Berkeley, and the seminar series today is going to be from Dave Sapsis from CAL FIRE, who I'll introduce in just a moment. Before we get started, I want to go through some housekeeping. First off, thank you to the sponsors of this series. This series is sponsored by the Fire Research Group and the School of Engineering at UC Berkeley, and also the University of California, Merced. Co-organizers of this seminar series is Professor Jeanette Cobian and Crystal Colden both from UC Merced. And we will be announcing some more changes and other partnerships, but at the moment we are coordinating with the California Fire Science Consortium, who helps with advertising and some other features of our series. So now that most of you have gone on, just want to talk about the logistics. On the bottom right-hand side, you see the Q&A button. Unfortunately, we don't have live audio and video during the talk, but we do have the Q&A box. Please go ahead and put your questions in. We'll go through them after the end of the seminar, and we'll also record this so that people can view after. So I am really pleased today to introduce Dave Sapsis. He's got over 35 years of experience in the field of wildland fire science, and he currently serves as the Senior Fire Scientist and Research Program Manager with CAL FIRE's FRAP, or the Fire and Resource Assessment Program. And he is the project lead on a number of wildland fire mapping and GIS projects within the state. And for those of you who have worked in an area of wildland fire in California, you probably worked with or seen Dave's name on a number of projects. So we're really happy to get this update on the FRAP program and how they're working on hazard maps. And I'll leave it to you here. Thanks again for coming.
Thanks so much, Michael. That's great to be here. And I've been a big fan of this seminar series, really been intrigued by the mix of topics that have been approached. And I think it's really appropriate given kind of where we're at here in the West and, you know, in 2021. I do notice that Dr. Gollner and I were fumbling around to make sure that the screen presented off of my PowerPoint, and it looks like that the title somehow got extracted or removed. In any event, it's using localized severe fire weather inputs in statewide hazard mapping in California. So the real focus here is going to be on those weather inputs, but I'm gonna give a brief outline, kind of setting the context of where this work is going. And hopefully everybody can see this and kind of, at least some of you recognize the area. This is, you know, I'm a Cal grad. My parents were Cal grads. I want to, you know, give a shout out to the forebears to Dr. Gollner in mechanical engineering and combustion science, Dr. Pat Pagney and Brady Williamson, who really reached out to the forestry and wildland fire community when I was a student at Berkeley and started some of that cross-pollination of disciplines that were pretty highly, you know, separated. And, you know, I think that the intervening years have been really fruitful on those kind of collaborations. And again, I really hold those years that I spent at Berkeley dear to my heart. In fact, I think if you guys can see my cursor right there, that's the life science building. That's where I met my future wife. So not only a good career was launched there, but a good life as well. So on to an outline again, give a little bit of a history about Fire Hazard Severity Zones. It's a unique kind of product that has some specifications and history that I think warrant some contextual discussion. A little talk about where we're at with the current data set and how it has performed. We're going to talk about some broad updates with regard to the model updates that we're pursuing currently, and then go into some details with regard to these enhancements of bringing local fire weather data into the mix. And then we'll all end with just a brief rundown on what the schedule looks like as we roll these data in this project out. So the history of FHSZ is kind of the story of two large urban conflagration, high damaging fires. The first one in 1980 in San Bernardino, where a fire came off the San Bernardino Mountains under extreme Santa Ana winds, not surprisingly. caused 4 fatalities, destroyed 273 homes. A number of the homes were identified as being largely ignited and destroyed because of their wood roof structure. Out of that came legislation and state statutes, PRC 4201 through 04, authorizing CAL FIRE to make designations for fire hazard severity zones on state responsibility lands. These are the roughly 31 million acres of open watershed lands where CAL FIRE has fire protection responsibility. The first zone model used sort of a modified National Fire Danger Rating system, sort of the estimated number of days in a typical fire season that exceeded a threshold level of a NFDRS index called burning index. And out of that, we classified 3 zones, moderate, high, and very high, nominally to coincide with 3 existing roof class assemblies, A, B, and C, with regard to sort of matching a design mitigation to a hazard level. So that was the originating fire and legislation for authorizing zoning on SRA. In response to the 1991 Oakland Tunnel fire, again, extreme Diablo winds, large number of fatalities, at the time, sort of a high water mark with regard to dwelling units destroyed. Local legislation by Tom Bates, Assembly Bill 331 was passed, and it codified the statutes for zoning hazard zones in local responsibility under the government code. And that was first done under a relatively simplistic kind of a scorecard model using 4 criteria: fire history, fuels, slope, and weather information. It wasn't really until the emergence of a urban wildland interface code development group in the state fire marshal's office, roughly in the 2004 time period, that FRAP got involved in this. We had done some statewide mapping of hazard, and we were brought in to build a statewide integrated GIS model, a single model designed to fulfill both of these statutory requirements. And that manifests itself in a GIS based model roughly in the 2007 kind of time frame. And those are the current existing maps. If anybody wants to go and look at that data, it's available via both maps and GDB data sets on the State Fire Marshal's website, as well as a web viewer that I have a little cutout picture of in the upper right that's available at the website below, and it's hosted by us here at FRAP. So just a brief little intro on the 2007 model. It was wildland centric, but it made a very explicit endeavor to map non-wildland developed urbanized areas, because that's where we were seeing, like with the Oakland Tunnel fire, like with the Panorama fire, basically wildland fires emerging into developed or urban zones, wildland urban interface, and causing lots of damage. It's important to recognize that the model uses a climax fuel construct, so short-term fuel modifications don't show up in the model. It kind of has a long time horizon, given that one of the main thrusts regulatorily was these new urban interface building codes designed to harden structures and make them ignition resistant. It didn't make sense to zone or to require a house to be based on relatively temporal sort of fuel conditions. So that's one of the real reasons why FHSZ has some uniqueness with regard to its use in sort of determining hazard. It's sort of a long range view. The model, largely because of limits of data descriptions and spatial specificity at the time, decided not to use specific fire weather inputs. It used basically a stock severe set of fire weather inputs to do fire behavior calculations. And I'll explain exactly what those were a little bit later. But that really is foundationally a big change that we're making here in this new remap. At the time, we built in what we thought was a fairly clever but simplistic firebrand distribution model to account for firebrand transport and mass transport ignition mechanisms in urban fuels. We all know that these are really, really important mechanisms of spread. Urban fuels tend to be highly discontinuous. Oftentimes structures themselves don't ignite with the passage of the fire front through the light and porous vegetation fuels. And so that firebrand transport was viewed to be critical in building a model that kind of emulated what the driving mechanisms of spread and ignition were in urban areas. But it was really simple. It basically didn't have direction. It was a negative exponential decay function from a source cell and kind of radiated out like a donut. And what you'll see later on in the presentation is how we're addressing improving that model to account for localized winds. But in general, the model kind of scaled to produce very high bands from roughly a quarter to a kilometer in depth. And on the first picture, you kind of saw that as it came off of the Berkeley Hills and about halfway down through campus. Again, at the time, we built those zonings and calibrated them on some known fire events, and that's the same process we're doing with the remap. Here's basically the data that exists statewide. On the left is the SRA data of the roughly 30 and plus million acres. 12 and a half are in the very high zone, 10 and a half in the high zone, and roughly 7 and a half in moderate. Within the constraints of mapping in LRA zones, and again, these tend to have different kinds of landscapes. They tend not to be wildlands. We made recommendations for 865,000 acres in LRA very high. And that amounted to being roughly about 190 unique jurisdictions adopting those local zones via a local ordinance. With regard to performance, I think this is looking at structure damage from our DINS program, where we've got spatial accounting for structure damage from wildland fire with an overlay on FHSZ zones. And what you see here is a total over since 2013, so 8 years of structure damage totals here, almost 50,000 structures. The only ones that are being accounted for here are either destroyed or significant damage. There are other classes of damage level, but for the purposes of this summary, I'm looking at destroyed or significantly damaged. And you see, 2/3 of them are occupied in areas as zoned as very high. That looks pretty good. And in fact, then 14% in high in the orange, 12% in the moderate category. There are, in this data set, 5% or about 2,500 plus homes that were in unzoned areas. So the take home kind of here is FHSZ relative to predicting where house loss is occurring is pretty darn good, except when it isn't. And when isn't it? And it's almost all dominated by a single fire event in 2017, the Tubbs fire. There's an outline there on the a map on the right. The fire perimeters in purple. The FHSZ zoning kind of in the pale colors represent SRA areas in moderate and high, and there's a very high zone inside the city, inside LRA. So at least with regard to in 2017, we had a fire event that really pushed itself outside where we had zoned. And this has been a cause for concern. Why? Why did it occur here, and why didn't the model capture it? And in retrospect, we think we weren't really adequately accounting for the influence of severe fire weather and the expression of climate on fire hazard. And that's why we're really addressing it through a very, purposeful sort of approach here that I'll dig into a bit. This is another interesting graphic with regard to the overlays of structure damage by housing unit density. And this is kind of in contrast to some of the recent papers that have looked at housing density relative to wildland urban interface fire loss. what it shows is most of housing density losses actually occur in high density areas, urban areas, density 4 classes, 1 house per acre and greater density. There are sizable portions in that very, very low density class as well, but it's very, very mixed. And again, some of the papers are basically looking at sort of a different performance metric. Basically, what kinds of land do you have house loss in? And that follows the general burn probability function, where open space wildlands that are conducive to fire spread and have high burn probabilities also have, when there are houses in them, tend to have house loss. But these data definitely do show at least some sort of a, a multi-peak kind of distribution, where when fires do encroach into urbanized areas, you get concentrated losses. And I don't think anybody, that's listening here needs to be reminded of events like Butts or like Paradise or the various other urban conflagrations that California suffered over the years. So focusing on where we're going with these new updates, I'm going to go over a few different bullets kind of quickly, and then the ones in yellow we're going to dig into. We've got updated burn probabilities for wildland areas, inclusive of the 2020 fires. We thought that was prudent since, we're just getting around to finishing up the model now, and we burned roughly 4.3 million acres last year, or over twice as many acres in wildland fire in California as in the modern period of record, that we would include that data in our calculations of burn probabilities. And it's important to note that, like any classic quantitative hazard product, burn probabilities is basically a multiplier. You have probability times intensity gives you a quantitative estimate of hazard. So I haven't included a graphic, but I do have it available if folks are interested in looking at what the input burn probabilities to the new model are. We've updated our fire environments footprint. I'll talk a little bit about that, but again, the model really bifurcates along a wildland urban distinction. And these fire environments are how we describe that portion of the landscape that we do not have data to describe in a wildland environment, and use classic wildland fire behavior techniques for characterizing hazard. We've used a number of different data sets to get the best idea of where that urban wildland distinction exists. For those urban areas that we defined above, we've got some updated vegetation density. That's an important criteria or factor that we use in the urban zoning. We are going to be including slope in the urban submodel after sort of review of our older model, and seeing some high slope areas tending to have greater fire penetration into. And again, the real thrust of this talk is going to be on localized fire weather. It's being used on both the wildland and the urban side, and how that localized weather, and in particular wind data, feed into a new firebrand production and transport model. So bringing local weather in, we are using data provided to us by the Desert Research Institute, using CANSAC procedures. CANSAC is the California and Nevada Smoke Advisory Council, and CANSAC provides the operational downscaled fire weather forecast for both the North and South geographic coordination centers. These are basically the fire and intel centers that exist in Redding and Riverside that provide support information for fire operations. So DRI has a long history of doing fire weather for operations. The modeling routine that we used is a weather research and forecasting reanalysis model. It is a numerical downscaled model, otherwise known as WARF. And what we've got is a 16-year, 2-kilometer grid reanalysis that gives us hourly measures of fire weather 24 hours a day, 365 days a year. And we ran the main fire weather variables that we would extract from this for our hazard uses here through a bias correction process, by which compare sort of in a quantile or in a cumulative distribution fashion values that are produced by the model, and then compared to actual surface weather stations and make some adjustments there. We felt that was an important process. I do show a graphic on the right. This idea of using reanalysis for hazard actually got its start with work that I did with a number of colleagues under sort of the sponsorship of the California Public Utilities Commission. And this is just a graphic of one of the ignition metrics that we developed at the time, looking at a sort of overhead utility ignition potential. And it used explicitly used this WRF downscale data, and you can see the kinds of patterns that you see, kind of showing itself geographically, at least in this index. But that's where we got our start, and sort of went down the road of working with DRI to build us this reanalysis data set. So what do? We've got this 16-year hourly data set. What we need to do is create a localized weather selection set that represents severe fire, because we make the assumption that most of our bad fires that cause our damage, the manner in which we want to characterize weather's influence on hazard, is when weather's really bad and the hazard's really bad, because those are the kinds of fires that cause that become large fires and cause lots of damage. So we did a two-step filtering process, first using a 90th percentile quantile cutoff on the NFDRS index called energy release component, run off of fuel model G. It's a common kind of metric or statistic used to filter out dryness. When you apply ERC to fuel model G, it kind of weights the outputs as the fuels are considered uniform across the landscape. They're highly sort of weighted towards dead fuels and larger diameter classes. And so we selected the top 10% of days. We actually used the GridMet data set to do this initial filter to say, what roughly are the worst 336 days of the year with regard to dryness, as based on this metric. From that subset, we then applied the DRI analysis, an additional additive filter to look at really severe fire weather days. And to do this, we used the Fosberg Fire Weather Index. The Fosberg Index is designed to be roughly linear with fire line intensity. And so, we know that intensity really is a good measure of magnitude of fire's capacity to do damage. It's highly correlated with observable characteristics like flame length, and all other things kind of equal, a more intense fire spreads faster and can do more damage. And so what we did was we took amongst those, roughly 16 years times 36 days, we took the top 5% of Fosberg fire weather records at the hourly level. And that is our selection data set. You can see in the net outputs here, you've got quite a bit of variability across the state. Very, very high values in Fosberg, in the southern part of the state and in the desert region. Lots of fairly uniformly moderate to mid-high values, kind of the browns in highlighted areas of mountainous terrain, and some areas of really relatively low values along the coast that have persistent moisture inputs from the Pacific Ocean. And so when you do all of that and you really are still filtering and filtering and filtering, selecting for severe fire weather, they still don't amount to being all that critical. That doesn't mean that they don't have their events, but they don't at that cutoff level. So again, just going over exactly what I said, we applied these quantile filters successionally. First the ERC for dryness, then the 95th on Fosberg for specifically fire weather. Fosberg weights fire weather winds, relative humidity, and temperature. Those are the three variables that go into its calculation. And we wanted to make sure that we were significantly capturing wind as a strong influence on hazard. And again, Its use here in the wildland side is fairly simplistic. I told you that we ran fire behavior analysis based on fuel model and slope class against a stock or fixed sort of fire environment conditions. And those were 3, 4, 5, and 70% moisture contents for fine 110, 100-hour fuels and live herbaceous and woody fuels, and a 7-mile-an-hour wind speed. So it's really actually conditions that are quite dry, but not all that windy. And by using a localized quantile cutoff of Fosberg, we can make adjustments to those stock fire intensity values to reflect their divergence from these stock values. We can basically represent those input conditions as a baseline Fosberg and then look at the deviance from that value to the 95th percentile cutoff and make an adjustment to flaming on the wildland. Now I want to get into how we're going to use the selection set for our urban modeling and driving the firebrand submodel. All winds in the final selection set were translated into wind vector classes. So again, every one of those hourly weathers that met these two filters were put into an associated frequency distribution of wind vectors. We've got 10 mile an hour speed classes that we've classed them into, and 12 azimuth classes for a total of 60 unique kinds of vectors. One of the things I want you guys to take home with from this is that fire winds are highly variable in both direction and speed. I've got some tables here of both direction and speed, directions on the y-axis, speeds on the x-axis for the 4 pilot counties that we're working on developing the pilot model for. And you can just see, we've got highlighted pink values that are relatively, sort of unique. But for Butte County, you have the dominant kind of wind vector across the entire county anyway, here out of the north-northwest at 10 to 20 miles an hour. That's just kind of how it all shakes out. Again, these tables represent the average of all of the WRF cells in each one of the subject counties, but it just gives you an idea, even across the counties, how variable things are. Now, again, it does appear that the selection set is dominantly being dominated by relatively low wind speeds. I think it's important for the listeners to kind of register the WRF outputs of wind speed against what they might be thinking based on surface observations. WRF basically produces an instantaneous wind that's largely analogous to a sustained wind, and it's averaged over a 2-kilometer grid cell. So, there's, in particular for rugged terrain, there's going to be quite a bit of variability in those. So these values might look a little bit low, but I think the real important thing is, do they register their variability against other places in space, such that when we use them to influence our hazard model, they're working in a fashion that shows what the actual localized fire winds do to contribute to hazard. Here's a graphic that looks at direction across space within Butte County. And, bear with me on trying to understand these, but like if you were to basically look at, this is kind of saying at the proportion of winds coming out of, and these are missing this, but these are the 12 cardinal directions starting from north, northeast, east. So this area of this canyon, or it is a canyon, but this area of Butte County has its highest likelihood of fire weather winds to come out of the northeast or the east-northeast. Conversely, down here in the lower right, the western part of the county gets its winds largely out of the northwest. Lots of the counties fairly, uniform, and it's got, a relatively wide distribution of wind directions captured in our selection set. Here's the same sort of thing, but looking at wind speeds. You look where are areas dominated by wind speeds, irrespective of direction, less than 10 miles an hour. Um, you know, 10 to 20 miles an hour. Again, really large portions of the county are dominated by this wind class. When you get up to Butte County, there's relatively low frequencies. In fact, there are no wharf cells in our selection set greater than 50 miles an hour, and only trace ones above 40. But again, just some graphics to give you an appreciation for how variable these wind vectors are. Here's a couple of other real similar ones, but this is Riverside County. They have higher winds typically down there. But again, if you're looking for concentrated north winds, they occur over here. Concentrated east winds here. Concentrated northwest winds over here. Really quite variable in different portions of the county. And here's the analogous wind direction distributions. What I'm going to do now is actually focus on some individual wharf cells and what the distribution of the wind vectors are for that particular wharf. And to do that, we've created these kind of two-way wind rows documents. So for this cell in the northeastern portion of Butte County, this 140-408 alludes to the XY coordinate system from our 2 kilometer by 2 kilometer grid from wharf. What you get here is a fairly classic Northern California Diablo wind kind of event. You see the majority of the winds come out of this east-northeast winds. There are some small amounts of vectors. And again, these circles represent the proportional amount that vector occurs in the entire selection set. But, over 70%, so that's the 75% circular mark here, over 75% of the fire weather winds by our technique come out of this single direction. And in fact, a good 25% of those are in the 20 and 30 up to 40 mile an hour category. So this is just one example. We've got these wind vector distributions for all wharf cells. I'm going to go through a few just to give you a flavor for how different they are. And I think there's insight into that, because we tend, at least anecdotally, to simplify fire wind patterns into relatively simplistic kinds of generalizations. Here's a vector location from the southern eastern part of Butte County, and it's a much more mixed bag. And in fact, its dominant or mode wind is out of the south and encompasses up to what looks to being about 55 or 60% of it is all out of the south. And lo and behold, it isn't all that strong. It is what it is. And I think it's important to recognize once I tell you how we're informing our firebrand model, that we use all of these data to distribute firebrands, because all of these data represent fire winds. Here's one from eastern Sonoma County, very monotonic, again, very Diablo-ish, a little bit more oriented a little bit rotated out of the north. It goes into the northeast vector class, but you're getting 90% of your fire weather winds for this location in Sonoma County out of this one direction. And again, they're dominated by the green band, which would be in that 20 to 30 mile an hour. We have created these distributions for every piece of the state. Here's one from, I'm sorry, I went the wrong direction. Here's one from Riverside County. Again, strong Santa Ana influence here, but there are some significant winds out of the due east and some very modest occurrence values and relatively low values out of other directions. So how are we going to deal with all of that relative to using those for firebrand lofting and distribution? We've got a cell-based generation of brands lofted based on fuel type and fire intensity, which follows generally the findings of Frank Albini. where the numbers lofted would be the sort of brand loft potential for that cell times its probability of burning times a scaling factor. Once you start adding in this P fire, these values, you know, at an annualized level are pretty darn small. I'm going to show you an example where it's basically about 0.4% or 4 in 1,000 likelihood of the cell burning. So we add in a scaling factor so that when we do our brand accumulation, we're not dealing with lots of very small fractional numbers. One of the interesting and innovative things that we're working together with Joe Scott at Pyrologics is deriving these firebrand transports from a focal sum kernel, and I'll explain what those look like and how they work, that distributes the source brands downwind according to some generalized negative exponential decay and a scattered pattern. Basically what these look like is kind of a fan, and I'll describe those with a graphic. We've created kernels for 100, 200, 400, 800, and 1500 meter maximal distances. And again, the orientation of the kernels would follow the wind vector distributions as outlined in those windrows or that I showed you for discrete dwarf cells. So there's a total of 60 size direction kernels, and the kernel assignment will depend on the winds, fuels, and fire type. We're still working through the lookups for all of this and still working through their coding within GIS, but I can show you at least schematically and stylized how it all works. Here's a single vector with a 400 meter maximal distance occurring as a result of a east-northeast wind. The brand source cell starts here with a source of 3,800, where the potential for the cell was 1,000. The likelihood of it burning was 0.0038 or 0.38%. And we use a 1,000 scaling factor, which gives us a total lofting of 3,800. And they get distributed downwind from this dominant wind coming from the east-northeast in this direction at this kind of a pattern. Most of them occur at higher density close to the source cell, but actually, since there are larger numbers of cells at certain distances as you move further and further away, the density of firebrands decays per cell because they're being spread across a larger footprint. The actual mode for total numbers of cells follows Albini's roughly 1/3 the max distance. It seems like one of my slides might have gotten missed. I wanted to show a kernel, and if we have time, I'll have to go to another screen. Here's an example of a larger, from the same direction, an 800 meter east-northeast wind. Again, the source cell following the same sort of pattern. So what's going to happen when you run this focal mean kernel across this entire landscape, there's going to be brand sources coming from all portions of the wildlands. And because this is a focal sum, it's going to add up those brands into where they land and sum them from the source of all torching cells, all of their originating locations. So we're at 3:40 now. I think I will have time to jump over and show you an example of a brand. I do want to go over a little bit over the model rollout, but that was quick and dirty how we're approaching bringing in all of this climate and localized fire weather into our mechanics of doing our FHSZ modeling. The rollout's looking kind of like this. May 2021, the 4 pilot counties draft data will go out for a review and calibration workshop, and then a relative short feedback time from the locals. Again, the pilot counties are Butte, Sonoma, Tuolumne, and Riverside. All 4 of those counties have had large, pretty damaging recent fires. For the most part, all of them, with the exception of Tuolumne, have had really significant wind-driven fire events. Of course, the The rim fire in 2014 was unique in its regard because it had a couple of plume development occurrences that drove it to the east. But again, it's a good subject area of sort of being a mid Sierra County. It's got a lot of wildland urban interface in the Tuolumne City and Sonora area, and deep canyons and fairly typical kinds of fire winds for that portion of the state. The other counties have all had, you know, a number of dramatic urban conflagrations that we can use for calibration. At the same time, we're going to package up all of the data and the methods and send it out to our technical advisory committee, of which Dr. Goldner is an esteemed member of, and they're going to red pencil what we're doing here and tell us, you know, what looks strong and what doesn't. And we're going to take into account those comments very seriously and work with the technical advisory committee to make any required model changes to give this model, you know, the scientific chops that it deserves. I believe that there are 12 or 13 members of the technical advisory committee, including Dan Gorham from IBHS, Joe Scott from Pyrologics, Chris Lautenberger from REACTS, Alex Marangades from NIST. It really is a all-star group of scientists that know a lot about what we're trying to do here, and we're going to rely on them to make sure we're not doing anything wrong-headed. After sort of incorporating model changes in our final calibrations, we're hopeful that this thing is going to all run in package and not have to do it tiled like we did previously, because that ends up causing some issues with regard to sort of adjacent areas and buffer modeling. But by the summer of 2021, the draft models will go out statewide, delivered to CAL FIRE units for the SRA review process. And by late summer, early fall, we hope to have the SRA zones adopted through the Title 14 regulation process that's required under statute. Once we get the state model done, and if you know that might involve some revisions to the map based on local knowledge and fixing adjacency in the map, because where you fix the model in one spot, you know, it impacts areas around it, that we are able to generate a draft model at the statewide level to then carve out for all of local responsibility areas by early fall. And we're going to put these up on a web tracker and have parallel review and processing to hopefully expedite the review and final sort of buy off by local jurisdictions, and again any edits that may be required due to data problems or a rule that just isn't working in that local area. So again, by fall, we hope to have up on the web all the data going out to local jurisdictions and their stakeholders engaged in a formalized review and data tracking system to produce the final consolidated maps for local responsibility areas. Those will likely be delivered at the county level upon completion of all of the individual jurisdictions. Some of these counties are more complicated than others. I believe LA had 37 cities with a very high recommendation in 2008 or 9 when we delivered it. Other counties are, you know, just there's more modest areas of LRA, and that makes the review process a little bit more simple. That's where I want to go to questions, but I did want to see if I can show you the kernel. Let's see if I can. I think what I do is I go to this, stop share. This should only take me a second. Are you guys seeing a new screen? Michael, can you verify that?
No, we're not. I was muted.
Oh,
We're not
sorry.
seeing another screen.
How about now?
Yes.
Okay. So I'm trying to show it. It might not want to show it on full screen size. So that at least gives you
That's
a bit bigger. So this is what this density focal mean kernel was. And again, I want to give a shout out to Joe Scott and his GIS folks for solving this. This is a brand kernel for 800 meters with a west wind. And two things I want to point out. All of these little values are the fractional amount, and they sum to 1. And that says as you move this as a focal mean product across a landscape where you're producing firebrands, it produces for the relative aerial location, its position for, let's say, this cell point, and it says 0.00313. So that means 3% of whatever gets produced when this cell passes over a subject cell. In the example I gave you, it was 3,800 being produced, that it would give you the right amount. So it's the manner, it is the GIS tool that we use to fractionally distribute firebrands from a source cell with a given distribution pattern. The other thing that is counterintuitive to this is for a west wind. A west wind comes from this direction and blows left to right. And yet the pattern of distribution of this thing appears to be driven by a right to left process. Well, that's the counterintuitive part of a focal sum. It basically produces the mirrored image of the distribution on the source cell when you float this over, as it does, basically these focal tools are community-based tools. They say how around a particular subject cell do you calculate some kind of an influence or relationship. So this is the development of the unique GIS tool or vehicle by which we are then applying to those individual wind vectors to distribute their input into firebrands. And these firebrands then get accumulated on the urban landscape and totaled up, and they end up being foundational to the scoring. We don't know that the final zones will go all the way out to the most lowest number of brands. In the past, we set a threshold level of brands needed to make it into the moderate zone. And again, our model produces the full suite of 3 zones everywhere, even though we're only statutorily required to deliver a very high zone for LRA. So that's pretty much the talk that I have. I know I blazed through a lot of things relatively fast. There's a lot going on in the model. I did not show you another slide, which I suppose since I have it here, I could do. I could show you this slide, which is kind of FHSZ looks like a modern vehicle when you pop the hood. It gets a little complicated fast there. But we do keep track of everything that we do in the model, such that when we have an area that looks wrong, we've got a means by which we can work backward through the model to see where that error or perceived misalignment is coming from. There are a couple of other things that we're still in the deliberation phase that are fairly important with how the model is going to roll itself out. But it'd be premature to really address those before we've had a time to implement them in GIS and evaluate what our decision points will be. But I do want to at least make everybody know that the draft data that's going out to the technical advisory committee and the internal review is draft. And, we're doing our best to produce what we think is a logical and sound model, but really do want to hear from both stakeholders and the technical advisory experts. So with that, I think I will go back to
questions.
We've
got some great questions. So thank you very much for your talk. And we will start off with some of the questions here. Yana Valakovich has the first question. How well do the zones capture the lightning ignited fires in the Coast Range of 2020?
Yeah, that's a great question. And in fact, there's some ongoing work with some really good climatologists in the Pi Regents research group that's funded by the EPIC program out of Energy Commission that's looking at these weather profiles. And basically the answer is we don't. That was a little bit of a weird kind of event. They don't seem to occur with super high frequency. The last one that really registered like August 16th was June 20th in 2008. They really are important in determining certain kinds of fire year events where you get this saturation of ignitions under dry conditions. And those fires they're scattered across the landscape so distributed and so remotely, and so many of them, that they end up growing large, producing lots of smoke, and doing whatever those kinds of fires do under the ambient conditions. And in some cases, because they're persisting and active for months upon months, that eventually some really severe fire weather occurs on them and they have blow up runs. We were not able to extract from our weather set the unique meteorological conditions that drove that. By the same token, the 2020 fire burn probabilities are being influenced by the 2020 burn perimeters. So those areas do show up as being, because they just burned, and our period of record in that analysis is 30 years, that they are leveraging those areas with respect to burn probability. But it's a really good question, and it's something that I know that fire weather meteorologists are trying to find better sort of signals on what kinds of drivers are. And it was a really unique kind of event. You had a whole ton of moisture sitting off of the coast that then inserted itself across the mid northern part of the state, and with the immense heat that had been generated in this amazing total convective potential energy in the column, you just had lightning kind of come out the ears of the sky, as it were. And I think because they are extremely rare, getting a handle on not only the sort of meteorological mechanics, but also a statistical assessment of their probability is an emerging challenge.
So I'm going to jump order, but there's a couple questions which I think combined would be important. And basically they relate to, I don't think everyone understands that's not familiar with these maps. How is the outcome of this, these high or medium low fire hazard severity zones? How are those maps used, and what kind of data will be shared? I think people in particular are interested in the wind.
Well, this is government at work, and so everything we do is public. So the data will be made available, and in fact, we're going to package up a fairly comprehensive set of inputs, sort of secondary derived products and final products, into a GIS package for the technical advisory committee, and likely for other researchers that are interested in delving into it. With regard to the first part of the question, I didn't address a lot of this because the policy questions largely are managed by the project sponsor, which is the State Fire Marshal's office. And they've changed over time. We've gotten new legislation that has brought in new regulations assigned to the map designations. And in fact, there's like currently some legislation that's under consideration that would have the state required to deliver moderate and high zones for LRA, as just one example. In general, obviously the Chapter 7A building codes apply to anywhere that meets fire hazard severity zone designations. So all of SRA, irrespective of their zone classifications, and areas designated as very high in LRA. The Board of Forestry is working on a package of fire safety rulemaking currently that appears that it will also apply to that same footprint. So like you are seeing on the screen, anywhere that's got any of these kind of pastel colors, that's the FHSZ zones and SRA, as well as anywhere of these areas that are in dark red. Those are the LRA very high zones. Again, and local governments are certainly have the authority to create local ordinances that supersede any minimum requirements that are imposed by the state.
Thank you. So another question is, how do you measure fuel load and its effect in the model? I assume which fuel map?
Right. So we build that climax fuel type based on largely, I would say about 95% of the landscape based on our CalVeg land cover vegetation map that FRAP produces periodically. And, that basically assigns a CalVeg associated type and vegetation structure, sort of its density and size class, and what are the dominant kinds of species. And from that, we derive a lookup table to these climax fuel assemblages that then go into a fire behavior calculation to give us fire intensity. And again, that is a foundational input to the data and will be made available to interested parties.
Great. So there's another question from Stacy Frederick, and I know we're getting closer on time, so just remember, we'll continue and I'll save these questions in the discussion following the link is posted. So Stacy Frederick had a question on housing density. And is there any information on multi-unit houses versus single family houses for fire risk? Could multi-unit housing with buffers and home hardening be safer than single unit homes?
That's a great question, Stacy. Not in the demographics that we put together for doing our FE environments. We have been through 3 iterations of sort of where are houses and where is their fire hazard to develop geospatial models of wildland urban interface. And currently, if you were to look on the FRAP webpage, we've got the intersection of hazard from FHSZ and an estimate of housing units from largely derived from Landscan data with a timestamp of 2012. At the county and parcel level, there may be means by which you could tease out multi unit housing units and an evaluation. And I think there might that data is captured in the DINS data, so it might be a means by which to actually evaluate specific fire loss. But with regard to sort of fire exposure, where are there hazards commingled with various kinds of housing arrangements, I think you would have to go to the parcel data. And we've tended to not do that because extracting house information out of parcel data tends to be kind of difficult and not uniform. And so one of the standards that we try to apply to this statewide modeling effort is uniformity. Using the same kinds of data sets across space to not sort of build a apples and oranges kind of product. But that's a really good question, and I think it might very well be interesting with regard to exposure and loss. Is there a storyline that certain kinds of housing unit configurations are more resilient to fire loss?
So we're just about out of time, but I'm going to do one last question from Pat Pagney, because his name was mentioned in the beginning and is an author of some Firebrand models. So said, great job, Dave. Albini works for Wildland Brands. Did you do anything for urban generated Firebrands?
And I love Pat for this question. And if I'd had more time and probably been more deliberate in the description of the model, I'd been really explicit. We do not know anything about structure fuels and their contribution to spread here. And we really wish we did. But at the state 100 million acres, we just don't know how to populate that kind of information. And we look to some of the new scholars that are really looking at structural fuel influence on firebrand production. And there might be a way to do some linkages here that I haven't thought of. Alls I know is when I go out and I look at remote sense data or various kinds of geospatially explicit data for urban environments, making sense of what those structural fuels are vis-a-vis their ignition potential and then their subsequent contribution to spread after they've ignited, because we know those are important, right? Fire basically leapfrogs, and it's driven initially by vegetation, but in certain kinds of environments, it becomes dominated by structural fuels. And so, unfortunately, Pat, I don't have a good answer to it other than to recognize, and you probably were the person that taught it to me 30 odd years ago, those structural fuels are really important.
So one last time, round of applause, virtual, I know we can't hear, for Dave Sapsis. Thank you again for the presentation and update on the fire hazard severity zone maps. We're all going to join in now, so please follow the link for those that are able to attend. And I've saved, as best I can, this list of questions, and we'll call upon folks that are able to join there to ask their questions and have a little more informal discussion. Thank you again for attending. Also, if you didn't catch it, we do have a YouTube channel. The link is on the Fire Research Group website, and you can watch all of our past presentations. So thank you again for attending, and we'll see you on the next seminar.